First, welcome to this COPKIT project webinar, and thanks everybody for your interest on attending. And we hope it's very interesting for you. My name is Raquel Pastor from Spanish state-owned company SDF, and I'm the project coordinator of the COPKIT project, and I will briefly introduce the project before my colleagues, partners also in the COPKIT consortium, Alexander Poor from Leiding Technologies and Frank Mignet from Thales, Netherlands, who's the COPKIT technical coordinator, present you the topic of the webinar, that is data analysis and artificial intelligence methods for situation assessment for law enforcement analysts. I would like to inform you that this webinar is being recorded and will be available in the COPKIT website, that is, as you can see in the slide, copkit.eu. During the webinar, you can use the questions and answer panel to write your questions or comments, and we will read them at the end of the webinar presentation for the presenters to answer them. And with no more delay, I'm going to start introducing the project. The COPKIT is a project funded by the Horizon 2020 European Programme for Research and Innovation that is run by a consortium of 18 European organizations from 13 countries and with different profiles and expertise, including industry, academia, research and technology organizations, and 8 law enforcement agencies. The project also counts on 2 external advisory boards, the Ethical and Societal Impact Advisory Board and the End User and Stakeholder Advisory Board led by Europol. Regarding the project concept, it's worth mentioning that during a previous project focusing on strategic analysis for policing, the involved law enforcement agencies draw the conclusions that the strategic and investigative analysis were intrinsically dependent and that adequate exchange of knowledge between these different levels of analysis could improve their investigation and mitigation capabilities. They identified a gap in methodology and tools to enable the synergy between these levels of analysis, and this became the topic of COPKIT. So in COPKIT, we are attempting to close the circle between these 2 aspects of analysis, and we are producing means for both types of analysts to produce and share knowledge. And we call this approach the early warning, early action-led policing. And to achieve this goal, this main goal, the project has set 4 main objectives. Objective 1 is focused on developing the methodological aspects of early warning, early action-led policing, as well as producing requirements and approaches for the tools that are enabled for this approach. Concretely, we have chosen firearms trafficking and crime as a service as the 2 application cases to demonstrate and evaluate the methodologies and tools. As already stated, an important aspect of the early warning, early action methodology is the production of knowledge. Both types of analysts require tools helping them towards the production of knowledge. And this is true for all steps in the intelligence cycle, from data collection, information extraction, and the production of intelligence and new knowledge, up to the constructions of models supporting the assessment of the situation of specific threats, which extends into forecastings for the estimation of future threats. So our objective 2 is about developing tools, realizing capabilities for all these activities. And this, of course, is too broad. So we have to focus on specific subparts and specific data types, with a particular focus on techniques and tools that can benefit from the injection of domain knowledge by experts. Our objective 3 is about making the early warning, early action methodology and tools usable given the actual constraints of law enforcement agencies. On one side, in this approach, analysts' workflows will change and new interfaces are needed, allowing them to visualize and incorporate in easy way additional information. And further, given the emphasis of early warning, early action approach on information and knowledge sharing, it seems obvious that security is a strong constraint and also enabling law enforcement agencies to respect ethical, legal, and privacy constraints with respect to sharing. So we are working on the development of innovative solutions for technical infrastructure together with appropriate methodology and process in this regard. Finally, our objective 4 is about facilitating the uptake of our results by law enforcement agencies. For example, among other actions, we're working on an innovative way to allow the evaluation of the statistical performance of some of the tools on real data by law enforcement personnel at their sites, and also in the development of required training for analysts with different levels of expertise. And this has been the introduction of our smallest introduction of our projects. And now Alexander will start with the webinar topic on situation assessment support. Please, Alexander.
Hello.
Hi.
By definition, situation assessment helps to provide everything what we need to know, not to be surprised. This is not an easy task considering large amount of data and turbulent environments. But on the other hand, we have efficient algorithms and systems for data analysis. I would like to show our approach to development of situation assessment system in the COPKIT project. The system is based on assessment process. On the left side is this intuitive 4-step situation assessment process. The purpose of our solution on the right side is to support this process. The first step of the process is automated data gathering.
Right now, I think, yeah. But your presentation is not full screen anymore, Raquel.
Oh, no? I'm sorry. It's not? Sorry. Is now?
No.
No?
Okay, now it's okay.
It's okay?
Yes.
Okay.
No, one slide, previous slide, yes.
Okay, tell me when you need to go to the next slide.
Okay. As I mentioned, the situation assessment is a process. On the left side is the intuitive 4-step situation assessment process. The purpose of our solution on the right side is to support this process. The first step of the process is automated data gathering. The next steps are detection of the anomalies, their analysis, and analysis of identified threat. In next slides, I will describe each of these steps to show how our solution support it. Data gathering is the first step. In this step, semi-structured data are gathered, enriched, cleaned, anonymized, and prepared for further analysis. Semi-structured data in this solution are text with metadata, such as form, messages, emails, transcripts, documents, tweets. Almost all data can be transformed in this structure. In this presentation, we are using data from Account Forum published by Arizona University. In general, our solution is developed on the Python platform, but data gathering is based on 9 open source platforms that enables various data gatherings, such as flat files, databases, web pages, and data from REST services. It covers almost all data sources. This platform also provides data preparation functionality. Some of them, such as entity extraction, are also developed in other COPKIT projects. Next slide, please. Now we have data, and we want to get intervals with anomalies. The current version of our system supports this step in 2 ways. With time charts on the left side and automatically generated warning on the right side. The chart shows messages matching certain indicators. These indicators help identification of suspicious intervals. They are composed of keywords. For example, cybercrime group indicators is composed of more than 100 keywords. On chart, we can select intervals where these indicators are grouped. Generated warning on the right side also inform us about intervals with increasing number of matching messages and help us to find interesting intervals. In the presentation, we select interval in April 2015 and more messages than usual was related to botnet. Similar cockpit components, exchange, point detection, it's also developed in this project. Next slide, please. The previous step, identify interesting intervals. But this is not enough for LIAS to take some measures. Anomaly analysis provides details about selected interval in order to reveal new threats. The details are presented in conversation table, conversation graph, and automatically generated text. Conversation table on the top describes each conversation with parameters that help us to identify the most suspicious conversations. Under the table is graph with selected conversation. Why we select conversation? Why we analyze conversations? First, we have to know the whole story to understand meaning of each message. Second, some messages are too short for text analysis. Here, analysis of whole conversation provide better results. On the right side, you can find automatically generated text that provide more details about selected intervals. Next slide, please. The slide shows how this text is generated. The generating process is composed of entity extraction, association rules, rule selection, and transformation of rules into text. The concept is that rules with large value of parameter lift show extracted words that are heuristic for selected interval. This helps us to find new threats. The using of association rules is also part of other COPKIT component. In this example, the generated text and conversation analysis shows that main topic this interval is new version of malware beta bot and could be new threat. Next slide, please. In previous steps, we find suspicious interval with increasing number of messages related to botnet. In this interval, we found threat, which is new version of bot. We also find who developed beta bot and who want to buy it. Now we need answers on next questions. What is the history of beta bot? Who is the developer, the users? How many attacks was with beta bot in the past? And what risk is beta bot in the future? The answers of these questions can be found in various sources. This step includes new data, assessments, and visualization. We try to identify our solution. We try to integrate our solution with other systems, from BI to geographic information, and gathering data from new data sources. For example, we found Google Trends. In Google Trends that beta bot popularity increased from April to July, especially very popular in Poland. At the beginning, I mentioned that situation assessment help to provide everything what we need to know, not to be surprised. Proposed process and solution do exactly this. Next slide, please. Now, I would like to mention our further work. Conversation analysis is promising, and we will continue to improve it. Also, we will test new input data, such as emails and transcripts. We will also integrate our solution with internal law enforcement data to improve assessment. We will also work on new algorithms to improve identification of threats. Next slide, please. In the future, we will also develop two versions of solution, one in Python only and other in combination with other platforms such as MIME. At the end, I would like to show what we have learned. Integration of situation assessment algorithms into working process is crucial. The algorithms cannot be in a vacuum. They must be connected. It is easier to develop algorithms when their purpose is clear. Also, we don't need to build new solutions from state-of-the-art techniques. We can start from process and with basic techniques. For example, if you want to develop self-driving car, first we need a car. Here AI without car is useless. Next, I think that integration of our solution with other systems is a good decision. We have to take into account that all LIAs already have tools such as I2 Analyst Notebook, ArcGIS, BI, analytical platforms such as Python and 9. And they do not want to get new platform which change everything because they do not have enough resources to manage too many different systems for similar purpose. Next slide, please. Thank you for listening. And for now, this is everything from my side.
Now Frank is continuing with the next part.
Good morning, everybody. In the second part of the presentation, we will present another approach focusing on estimation of lower level characteristics for uncertain information pieces. Next slide, please. First, let's have a look at concrete questions that we target in the COPKIT project. As an investigator specializing in firearm trafficking via darknet market, you are confronted with a significant volume of offers which you need to analyze and prioritize. For example, you want to characterize what is the product sold in an advertisement, which is not trivial to automate. Raquel, I think the slide is gone. Oh, it's back.
Oh, sorry.
To automate this, you need to combine uncertain information about this advertisement, taking into account the ambiguity of the text. For example, text can be confusing between firearm model, ammunition, or both, and the imperfection of the tool that you use for the text analysis or the image analysis, if there's an image associated to this firearm. Even further, as an analyst, the computation of a form of priority for each of those advertisements would help you. Let's say the combination of a type of the firearm being sold, which is a risk, and some utility factor, which could be how recent the advertisement is. Those elements could be combined in a priority level, but this adds uncertainty elements to the estimation process. Now, if we look at it in a completely different setting, this time for strategic analysts, from a high-level situation awareness and sometimes for resource allocation, it's important to have an idea of regional risk for certain crime. As an example, in the COPKIT project, finding out if a region is favorable for the installation of conversion workshop for non-lethal firearms. Factors such as the presence of qualified individual, for instance, due to the presence of weapon manufacturer or metal manufacturer in the area, plays a role, but only in a probabilistic way. Not also that, as is always the case with criminality, the number of workshops that you may have discovered in that area is only a fraction of the actual criminality. When we look at those examples and those functions targeted in COPKIT, what they have in common is that you need to perform probabilistic reasoning with the domain knowledge of the criminology for your criminal area. Next slide, please. In the COPKIT project, we approach this type of question with probabilistic graphical model. So if I try to make an extremely summarized version of what that is, there are means to represent uncertain knowledge into a model, and those models have two parts. The structure, which you can see as the qualitative knowledge. For example, if you're interested in knowing if an advertisement is really selling a handgun or a hunting gun or an automatic rifle, The description made by the vendor is likely to express that, but with some uncertainty. On the other side, the market provides a classification of ads, provided or not by the vendor, but this classification, the quality of it may depend on the market itself. Some do better job than others. And then you see that the market becomes a contextual information, and you could even imagine that you add the image, the estimation of the image. And all this and the relationship between those various elements are constitutive of the structure. Which observable aspects are influenced or are influencing which others. The second part of a model are the parameters. Those parameters are conditional probability, and essentially they are the strength of the dependency. For example, given that the product really sold is a handgun, the likelihood that your natural language processing tool reach the conclusion that the product sold is a handgun is 0.95 in our example. Finally, once you have that model, you need algorithm to perform the reasoning. Those exist. Essentially, they're based on base rules. And the one we use, and this is also the most common one, is called the junction tree algorithm. And they then perform the reasoning that given this and this observation, what is the likelihood that the real weapon type is a handgun? That's a bit how it works in short. Next slide, please. Now, as you have probably gathered from the previous slide, the construction of the model is a key point. A convenient characteristic of PGMs is that they're very suitable for combining expert knowledge and machine learning process. That's what we call knowledge-constrained machine learning. By injecting domain knowledge, you reduce the model space to search through, and you make the machine learning more efficient. It means you need less data to learn the model. Remembering our example, the volume of darknet advertisement for firearm is certainly much larger than anybody would want, but it's still not millions. It's nothing to compare with cat pictures on the internet, for example. So adding the expertise of the LEA officer, of the criminologist, to label the data, that is a costly process, and then frugality in data is a serious advantage. In practice, the domain knowledge is mainly injected in the structure of the models for PGMs as the choice of relevant aspects and which aspect influence which other. And then the parameters are learned automatically. We've seen there's a couple algorithms to perform this task. Mostly maximum likelihood estimation when you have complete data. Another convenient aspect is that you can inject values even for the parameters. For example, if you know the confusion matrix of your natural language processing tool, that means how often is right, how often is wrong, which the maker should be able to provide you in theory, then you can use that confusion matrix directly. Less parameter to learn from you, and the ability to change algorithm easily. Finally, in some cases, the parameters can be defined by experts in a natural way. Next slide, please. I'm not going to be able to go through the model that we're using, that we take way too much time, so I will just show you a couple patterns that we use. Regarding our first question, you remember the goal is to assess what product is being sold. You have a couple ways to extract information, the analysis of the text of the advertisement, the analysis of the image if there's one attached to it, but both of those are imperfect. And as I said, often the market itself will offer you a categorization, but that categorization is also not perfect. And in fact, some markets are better at it than others. That market is where the context influences the quality of your information. And using such a pattern that we generally call the sensor model, you can combine heterogeneous and uncertain information in a robust way. All those tools that you've used, they're not perfect. So you need to be able to have a robust, in terms of reasoning, robust way to combine those information to reach the conclusion that what is sold is probably a handgun or an automatic rifle, for example, with a certain probability. And this is the goal of this type of pattern. Next slide, please. I've also mentioned earlier the question of making regional threat assessment for the strategic analysis. In this case, the amount of data is limited. You don't have hundreds of thousands of regions. That would make sense. At least with respect to the number of influential factors. There are many aspects, mostly pastel factors, but not only, that can influence such a risk. So it's a difficult case for machine learning. But I remember a few years ago being at a Europol workshop organized by Europol, in which they presented how they performed their their strategic threat analysis. And from this process, it is actually possible to deduce a probabilistic graphical model using the steps that are performed in such a threat analysis by a team of experts, with grouping the influencing factors that are defined by the experts into themes. And you can even incorporate the observed crime. Remember, this is only a fraction of the actual crime, so you need to have a specific way to do that. So what we can do with this is that we will not be able to create that model automatically, but with a little extra cost in formalizing the process that is being realized anyway by the analyst team for threat assessment, you can turn the result of that threat assessment into something that's computable, support uncertainty consistently, and is also a bit more maintainable. In this case, so it's all based on the expert knowledge. Next slide, please. So to conclude my part of the presentation, we've shown here a decision support technology that's quite versatile. It can be used for case analyst, for specific pieces of your investigation. It can be used by strategic analyst. There's something that you have probably gathered from the models already. Those models are extremely easy to explain because they refer about aspects in the real world, and therefore a domain expert, a law enforcement officer, can understand them. He can understand the probability that are given by the technology, and that's quite interesting, both from an ethical point of view, but also just because in general law enforcement officers, they like to know why do they get certain results. In terms of construction, we've shown an example of knowledge-constrained machine learning, which we think has quite a bit of future for the world of fighting crime and terrorism, especially for the lower volume crimes. So probably not the burglary, but crimes that are a bit more rare. And we have shown, of course, you've seen that the key is in the definition of appropriate structural patterns. And there you should be helped by data scientists, because good patterns are your key to facilitate the learning, and they increase the robustness. And I think that's, you've seen also they're a good way to mix very heterogeneous other tools, the result of very heterogeneous other tools. And that will conclude my presentation.